up to an even more electronegative atom, which is the oxygen, which would be happier in holding the negative charge, which adds, and well, all of this, like the second point, adds just even more stabilization to this molecule. Okay, so because this resonance structure makes this base more stable, HA is more acidic. The answer is HA. Okay. All right. Next problem. Would you expect HA or HB to have a higher chemical shift value on the proton NMR? Again, drawings are highly recommended. So what does it mean to have a higher chemical shift value on the HNMR? Higher chemical shift value means the atom is more deshielded, okay? The reason why we use deshielded is because we refer to the electron cloud that's shielding the atoms, okay? So each atom should have electron cloud surrounding it, acting as a shield, okay? So the answer here lies in the resonance structure for this molecule, okay? So I can draw this first resonance, like this first arrow up here. So because this is a neutral molecule, to draw a resonance structure for a neutral molecule, you would find just the electronegative atom. So we have oxygen here and we have oxygen here. They're the more electronegative atom in this molecule, but we can't really do any resonance with this oxygen, so we are only left with this choice right here. And there's a pi bond right here which can be moved up to the oxygen as a lone pair, okay, which is what I did here, and that would bring us the first resonance structure, putting the positive charge on that carbon and a negative charge on that oxygen, and then we can move this adjacent double bond over one more to give us our last resonance structure. And the key thing is this resonance structure. Do you see how there's a positive charge on this carbon right here, which is bonded to HA. This is HA right here, okay, and this is HB. Because this carbon has a positive charge to it, and more importantly, this carbon only has 6 electrons. Count your formal charges. This will be good practice. One common way, I should say, for a carbon to have a positive 1 charge to it is for it to only have 6 electrons. Yeah. Well, 6 bonds, I should say. What am I saying? 3 bonds. I am so sorry. Right. So, practice your formal charge. Okay. Carbon has 4 valence electrons, but right now it only has 3 bonds. So 4 minus 3 is 1. So it's holding the +1 charge. Okay. So and total electrons for it would be 6, so it is missing an octet because the carbon wants its electrons. It is pulling on the electrons within all the bonds to itself. Actually, it is pulling on the bonds, okay, so that it can have more electrons to itself, okay. And one of this bond is this bond to HA. Because the electrons here has been shortened, so the electron cloud has been removed from the HA. It is deshielded, okay, which would give it the higher chemical shift value. Now look at HB. Has the carbon that's bonded to HB ever hold any positive charge among these resonance structures? No, not really. It pretty much stays neutral throughout all of the resonance structures, so HA would have the higher chemical shift value than HB because it's more deshielded by this positively charged carbon cation. Okay, so yeah, HA would have the higher chemical shift value. Okay. All right, now let's look at this question. Would you expect HA, HB, or HC to have a higher chemical shift value on the HNMR? Using drawings as part of your explanation is again highly recommended. Alright, so again, higher chemical shift value, we're thinking about the atom being more deshielded. So I have all of the hydrogens separated here, so we can look at it parts by parts. Okay, so being deshielded means being next to like electron withdrawing groups, electron negative groups. So HA is next to an oxygen, which is an electronegative atom, so it is hogging some of the electrons within this bond right here, okay, which in turns make this carbon partial positive, okay? And because this carbon is partial positive, it is also hogging some electrons from this bond right here, okay? So HA is deshielded, okay? So do we understand how HA is deshielded? Okay, great. So let's look at HC. Okay, again, you can draw a resonance structure for this carbonyl group right here. Okay, draw it up, and then you will have your first resonance structure, a positive charge right here, a positive charge right here. So HC, you'll have this you'll have this positive charge right here. So because you have this positive charge on this carbon, it also wants to hog electrons within its neighboring bonds, okay? So which would make HC deshielded. Now you can draw a second resonance structure, which would be arguably the more dominant resonance structure, is by just putting the lone pairs from this oxygen down here, okay? So why this is more dominant is because, again, carbon with a positive charge means that it does not have an octet, but through this resonance structure, all atoms have their octet filled, and that is more important than whoever has to hold positive charge or negative charge, okay? Filling octet is an even bigger priority, okay? But because of this, oxygen has to pay the price. It is now holding a positive charge, okay? Like it is holding a positive charge. A positive charge on an electronegative atom is not making it happy. It is very grumpy. It wants electrons, but it is losing electrons. So in turn, it's taking electrons away from this bond right here. So it is making the set of hydrogen even more deshielded, okay? And with this resonance structure being more dominant than this resonance structure, because this has all octet rule filled up, you can imagine that the hybrid structure will more often look like this than this. So you can say that the carbon would have the partial positive way less than this oxygen having the partial positive. Does that make sense? So this oxygen will more likely hold this positive charge than this carbon holding this positive charge, because this is the dominant resonance structure since it fills all octet rule. Okay, but oxygen is paying the price, and it is de-shielding these hydrogens right here. Okay, now this comparing to this, okay, this is just electronegative. There's a partial positive here. Okay, and so it is drawing electron density. It is not as strong as this electron hungry partial positive on the oxygen atom. Okay, so the answer is HB. HB has a higher chemical shift value. HB has the higher chemical shift value. So yeah, so this is pretty useful for when you do NMR involving ester groups. Okay, now there will be times where it will be very hard to kind of orient these two oxygen. You can orient it this way, or you can orient it this way. It'll give you the same, I mean, let's say these two are different. They'll give you the same pattern, okay? Both of these will lead you to the same pattern. It's just you have to figure out how to orient this. And this chemical shift value will be the greatest hint you'll be given to how to orient this. Okay, if the peak integrating for the hydrogen